So yesterday, yesterday we went through this idea called dipole-dipole interaction. And I'm going to draw some molecules out and then draw the shapes of those molecules out based upon your shapes that we went through. Okay? So, these are called, these are three types of intermolecular forces of attraction. That's a long statement, but I don't know a way to state it any differently. Okay, so three types of intermolecular forces. Okay, so what is intermolecular force? It's just attraction between molecules. Okay? Got these molecules floating around. Do they attract one another? Yes or no? Okay? Some of them do, to some extent. All of them will attract. You know, you guys, big Star Wars fans in here? May the Force be with you. Okay? And they say that everything in the universe has forces that exist between them, and if you can somehow focus and have the gift to be able to access those, then that's a tremendous amount of power that you could have. And there's the dark side and there's the good side. All molecules attract one another to some extent. Some of them, you know, a big attraction because they've got all three types going for them. If they got all three types going for them, then there's strong attraction. They're taking all three of those and allowing those molecules to attract one another. So what does it mean by if they have attractions for one another and they're including all three of them? They have higher boiling points because they tend to want to stick together. And they don't let their other molecule friends escape. They say, you stick with us. Okay, don't go over there. That's bad. Stick with us. Okay? And then as more and more energy is added to them, then they'll start to escape. Like boiling point of water is 100 degrees. Okay? So at 100, they start breaking those forces. Okay? A lot at 100. Where at 100 for ammonia, they've already been into a gas. They're already to that point where they've broken those forces. Ammonia has a much lower melting point because they don't have as many things going for ammonia versus water. Okay? And so if you have all three of these types, you're good. If you don't have but one of these types, then your melting point and boiling point is going to be really low. Really low. Okay, how low? Lower than room temperature, which means they're going to be gases already at this temperature. Okay? Any questions or any thoughts on that? So, yesterday, those who were here, we talked about the first one. Number one was a dipole-dipole interaction. So, you're saying, I don't know what a dipole is. Well, dipole's like, Earth has a dipole, right? What's the dipole of Earth?
Force on something?
I mean, it just says, if you look at the Earth, it has a dipole.
It'd be the South Pole.
South Pole and North Pole. They're opposite sides, okay? And so we call those the poles because they're opposite of one another. Okay? But a dipole would be like a magnet, north and south. That when you have two opposite magnetic properties separated by a short distance. And that's what a dipole would be when you looked at a magnet. Okay? So the first thing I have to do is give you a definition of dipole. It's really easy. And I want to make sure I get the wording right so I don't have to erase anything. Has to be a short distance. Well, you can't get much shorter than when you look at molecules and the distance between two atoms that are bonded together. So,
What's that word after opposite? Charged?
opposite charges. So, what I'm going to do is I'm going to draw a couple examples of this. I'm going to go ahead and put another statement underneath this. Okay? And for us to have a dipole, you need to have this one thing happening for sure. And it is you have to have polar bonding. Must occur. Polar bonding must be present. Got to have it. If you don't have polar bonding, you can't have dipole-dipole interaction. It's not possible. So yesterday we had talked that to do this, you have to have a difference between the two bonded atoms. What would be the difference in electronegativity that has to happen? Between what, when you look at electronegativity and their differences, what does the range have to be? Well,
For ionic?
not for ionic, but for polar covalent.
Is that
.3 to 1.7. If it's in that range, we consider... Now, if it's up closer to 1.7, then it is a highly polar bond. If it's down by 0.3, we really can't say it's much of a polar bond. Okay? So the bigger the difference, the more polar the molecule will be. The bigger the difference, the more because there's a not an equal share. It's not an equal share. And if they're an equal share, then it's considered nonpolar, and it would not fit into this category. It does not fit into this category if that's the case. We'll give you an example of which one does follow it and which one doesn't. So you can have an example of one each. Okay? Here's one that has what we consider dipole-dipole interactions. Okay, yesterday I gave you some, all right, in your notes. So this is kind of a repeat. Now I'm drawing water the way it would look if the shape that I'm stating for it occurs. So it's bent shape. So if I look in my notes and I say, all right, what kind of molecule does water form? And you look on there and it says, there's two bonded atoms and two unshared pairs, and those are always bent structures. So bent structure means that you're going to have hydrogen atoms on one level, and then oxygen is going to be on another level. Okay, that's not on the same plane. Okay? What we did to show polar bonding, and this is what you missed yesterday, we always draw an arrow toward the element that has a higher electronegativity off to the side. Okay? And the tail of the arrow, we're going to put like, there's feathers on arrows, you know, and they help guide it. And these just show you that's the tail of the arrow, and they kind of give you an indication what the charge is down here. So if you look at the tail of the arrow, what's it look like? Positive.
If you count the arrow,
Yeah. So you want to count the arrow. So it looks positive. So when we did this yesterday, we said H to O, and H is 2.2, and oxygen is 3.44. When you look at the difference between those two, absolute difference, not that it's negative or positive, we always take the absolute value, it's going to be 1.24. That's in that range. So if it's in that range, I can draw arrows. The arrows always go toward the area that's higher share of the electron pair. And then what I'll do is just to kind of isolate the two different areas, I'll draw a circle around those two atoms, and then I'll draw a circle around the top portion of that molecule. And then down here I know that this area here is positive, and this area is negative. So this is a dipole. Two oppositely charged parts of the molecule separated by a short distance. Okay? So here I've got another water molecule. I'll draw the exact same way.
How do you know which way the arrow goes?
Toward the one that's higher electronegativity, because it has a greater share of the electron.
What if it's like three?
Doesn't matter what it would be, as long as there's a polar bond between 0.3 and 1.7, I will draw the arrow. Okay? So this side's slightly negative again, and this side's slightly positive. So, getting back to our definition, dipole-dipole interaction, it's when we have dipole and a dipole interact. So two different molecules, or two molecules interacting. How is this molecule going to interact with this molecule now if they're floating around? They're going to attract right here. This region, which is positive, is going to attract to the region down here, and that is your dipole-dipole interaction.
Boom.
Boom. So anything that has dipoles will interact and pull together. Now, something I don't know how much time I will go over with you, but there's some that you could have polar bonding and they won't have interaction. They won't have interaction. Just because they cancel out all one another. Okay? So, here's an example of where we don't have dipole-dipole interaction. Okay? So, this is where we do not have dipole-dipole interaction. Okay? It's when you have a situation where you don't have polar bonding. So it'd be like this. Te, which is in the same family as oxygen, bonded to hydrogen. And Te bonded to H. Te is a electronegativity that is 2.1 and H is 2.2. So what kind of bond, or what kind of covalent bond would that be? Non-polar.
Because that's 1 to 0.3, right?
0 to 0.3.
Yeah.
So I cannot draw an arrow on this one. I cannot draw an arrow. So guess what? If there's these floating around, there won't be any interaction between them, based upon just the dipole-dipole interaction. Okay? Any questions on that? Yes?
So will different levels have the same charge? Or will it have...
Here, you mean?
Yeah.
No, they'll all be, this will all be kind of the same charge all the way through. Because there's no, they don't have unequal share. It's only when you have unequal share. And that's where you get the difference of 0.3 to 1.7. Okay? All right, we got to move on. That was kind of a review of yesterday. All right? The Second one is called hydrogen bonding. This will play a big portion of what you guys are doing tomorrow and being able to explain what's happening tomorrow. Hydrogen bonding is going to be very big in understanding our lab that we're doing tomorrow. Not so much dipole-dipole interaction, but hydrogen bonding plays a huge role. Okay? So, when we have hydrogen bonding, it exists when hydrogen is bonded to one of three elements. Okay? And I'm not going to give you the definition for it. I think it's easier to just kind of show you. But I'm going to go ahead and show you what needs to be included to have hydrogen bonding. Well, of course, hydrogen you have to have. So, it's when hydrogen is bonded to nitrogen, fluorine, or oxygen. Okay? So, that is not the hydrogen bond itself. So what we have to have before hydrogen bonding can exist between two molecules. The first thing you have to have is hydrogen bonded to NF or O. It has to happen. If hydrogen is bonded to anything else other than NF and O, then it's not going to show hydrogen bonding. Won't show it. Okay? So if hydrogen is bonded to Se, no hydrogen bonding. Okay? If hydrogen is bonded to chlorine, nope. Bromine, nope. Okay, it has to be these three. So if it's not one of these three, then you can say no hydrogen bonding occurs. Okay? So I'll give you an example of what we did yesterday, something similar. It would be ammonia is what we call trigonal pyramidal. That's what it looks like. Okay, there it's got the three legs, there, tripod, and then it's got nitrogen above. Okay?
What is this one called again? Trinomial?
This is trigonal pyramidal. That one. Okay, so we got another one down here where you have one, you have a billion, or trillion of these floating around. Which means a lot. Okay? So, I'm going to show you where the hydrogen bonding occurs. Okay? And it occurs between this hydrogen of this molecule and an unshared pair of electrons, and I'll write that down. Okay? So, there's an attraction between this hydrogen and this unshared pair of electrons. Okay? This is the hydrogen bonding. You guys have talked about DNA before and talked about the helix structure. The helix structure sticks together by what's called hydrogen bonding. So that helix structure that unwinds and then is copied and then winds back up in the helix structure is because of hydrogen bonding. It's easily broken, but then it's easily reformed into that helix structure. Okay, I'll give you a second example because it's always nice to see several examples of this taking place. Okay, I'll do it with HF because HF would be another situation where you'd have hydrogen bonding occur. So here's HF.
Linear?
Okay? Right. It is linear. We can go ahead and show the arrow. I'm not going to because that kind of symbolizes dipole-dipole interaction, which this would probably be under that as well. So we got another one that's down here, H and F. Okay? This H is going to be attracted to what portion of this top molecule? The unshared pair. That's hydrogen bonding. I'll call H bonding for short. Any questions with that?
So
Yeah. Go ahead.
So when the hydrogen and fluorine bond,
Yep.
If you were to show it in the structure form, would you get rid of the two electrons?
These electrons here,
Yeah.
to show hydrogen bonding, you would just include those in there if you wanted to show it. Okay? You would not have hydrogen bonding on this one, though. If we had this one, no H bonding. If you have H bonded to Br. Because it's not one of those three. It's not one of these three that it would be bonded to. It has to be N, F, or O. No exception. Will?
Why does it go from unshared pair of electrons?
Okay. The reason why is because there's a huge difference in these electronegativities. Fluorine's 3.98, hydrogen's 2.2. So we have a difference that's high 1718, which means this becomes highly positive and fluorine's highly negative, which would create that dipole.
Yeah.
But we also have hydrogen, since it's highly positive, any unshared pair of electrons that are negative charge, it's going to be attracted to. So this area is still going to be highly positive, but instead of being attracted to one side of the molecule of another atom that's negative and positive, it's attracted to an unshared pair of electrons.
How come if it's attracted to an electron, the electrons, they just don't force fluorine that it's connected to give up electrons?
It's not strong enough difference in which to do that. It's not a big enough difference to do that part. So this is intermolecular forces are weaker than covalent bonds. They're weaker, but they're going to be present. So, all right, good questions on that. Last one is probably the easiest one, I think, to understand. I'm not going to give you a definition or anything like that. Let me go back. Let me go ahead and under number 2 write in the actual kind of statement that describes hydrogen bonding. Okay? And you can have that down instead of the example. When hydrogen of one molecule is attracted to an unshared pair of electrons on a second molecule. And again, this is going to be huge tomorrow, understanding what's happening to these liquids. Okay, so tomorrow you'll have 6 liquids, and you're going to dip these liquids into, with a filter paper, into a liquid, and then you're going to take them out and let them evaporate. Now, the ones that evaporate the most have weak intermolecular forces. Those molecules that evaporate, boom, they go really quick, evaporate, they don't have much holding them together. So they're not going to have much when it comes to these intermolecular forces of attraction. Others evaporate really, really slow. And when they evaporate really, really slow, you don't get much change in temperature. Okay? If you've ever put in rubbing alcohol on, or any type of cologne on, or perfume on, it cools the skin because it evaporates. Okay? And so evaporation is a process of cooling. When we sweat, it's our body saying you need to cool off. You need to start cooling off, and it opens those pores so that you can cool off. And evaporate takes energy to do that. And so these substances that evaporate fast, they don't have much intermolecular forces of attraction. Okay? So the last one, number 3, is called, it's the coolest one, name-wise, London dispersion forces.
Oh man, I thought it was going to be Garden.
Not that cool. That's only for Christmas, Garland. Okay? London dispersion forces. Okay, and this one has a long definition. It just, it's an instantaneous dipole created by motion of electrons. We're going to go ahead and give the definition, and then I'm not going to draw this one out, but I'm going to give you some indicators that will tell you what type of molecules will have London dispersion forces. Okay? So, these are really easy to see. Okay? If these are indicators of large London dispersion forces. So, I'm going to give you indicators. Okay, we're almost done. So these are indicators of molecules with large dispersion forces. And there's 3 I'm going to give you. Okay? 3 for now. We'll give them to you tomorrow. Okay? Give it tomorrow. See ya. Okay, so these are the 3 or 4 statements that would indicate we would have larger London dispersion forces. Okay, they are large molecules.
This is
So what I gave you here says these are indicators of molecules with large dispersion forces. Okay?
you're giving us.
Yep.
indicators.
Larger molecules. So if it's a larger molecule, bigger atoms that make it up would make it larger. Okay? So down here we could say larger atoms. So if we're comparing neon and argon, which of those 2 would have greater London dispersion forces? So neon is element number 10 and argon's 18. Which one's going to have larger London dispersion forces? Argon. It's a bigger atom. If you go down a group, they get larger. Okay? So bigger atoms. If you look down that list, neon, argon, krypton, xenon, and radon, they only have London dispersion forces, those gases. So the only thing that's holding them together is London dispersion forces, because they won't bond to anything, and so they won't have polar bonding or hydrogen bonding in those cases. So it's strictly just London dispersion forces for those. We're going to say longer molecules, longer chain molecules. You'll find out what we mean by longer chain molecules tomorrow, because organic chemistry allows you to link carbons together in long chains. So you'll get an opportunity to draw those out tomorrow. Okay? Another indicator is of these 3, larger molecules, larger atoms, longer chain molecules, is larger molar mass. So a lot of times you can't draw the molecule out because it's too complicated. And if you have to compare 2 molecules and you're given the weight of the molecule, called the molar mass, then you probably have a good way of deciding which one will tend to have larger forces of attraction. So those are 4 statements that you can look at to determine if they have larger London dispersion forces. Okay?